u is going to be less than this to the power 2, of course. I'm sure. But I want also one more thing. That is supremum of u. You already desired and z is less than constant 1 or 2. That's C1, C2. When z is on. Let's say this. So I need to prove, I proved this. But now, suppose my function is, suppose u is n equals 0. Fast. Say it is like r power 3. Suppose it goes faster than r power 3. We don't know whether r3 is the one that is given by the problem. We know it's less than equal, but it might be r3, so it's very fast. Then what you have is this. Then what you want to work with is, well, I will repeat this later in my text, but let me just write it like this. Then we want, so what we want is we want to look at the point, free boundary point, be very close to the free boundary. Look at gamma close to the z. So here it is. So very close. The reason for this is if I want eventually to look at the problem, and I want to say that free boundary here is smooth, then I have the technique I like this is to zoom it out. So my function, if the free boundary is something like this, if it's something like this, if I zoom it, then it will be something like this. If the free boundary is something like this, if I zoom it, it will be something like this. Because it's a cusp. So zoom it will be sort of line or thing or something. If the free boundary is, let's say, something like this, zoom it will be something like this. It has an angled plane, so it will be a plane, basically. So these are possibilities, and they can be much more nice. So these are the simple scenarios. Now, in order to study these problems, so what do we have? Let's say we zoom, and we have something like this. So how do you zoom? What is the technique of zoom? You have no information about free boundary. The only information you have that the free boundary is related to the function u is the boundary of the set when u is positive. So this one guy here is the boundary of the set u is positive. And this will be the boundary of the set when u is 0. The blow up of u is positive. So it means that the zooming technique of the geometric zooming is related to zooming the function. Because you cannot zoom the domain if you don't know what it is. But you know what u is. So zoom u to u0, blow it up, and study the function u0 itself. That's the way we have to do it. There is no other way to do this. Because these graphs, whatever graphs, these sets are not given to us. The only way they're given is implicit through the function u. So in order to zoom it, we look at very close to where the point, we have to look at the blow up regime of this function. So if you want to blow up, so you want to look at z and the free boundary u. very, very small. When I say very, very small, I'm going to have to limit. Okay, so the technique for this is, of course, scaling, because you cannot get to the point geometrically, you work with functions. So you look at, show the function. So how do you zoom the function? This is, of course, one zoom, agree? Because if I'm looking at point of radius r, like this, and if I look at this, it means I'm looking at the point of radius 1. If r is smaller, again, so I'm really zooming in and look at this. I'm not sure this is a good choice, but that is one choice. Okay? So one example is, let's look at the function. Just an explicit example. Let us look at the function. What kind of functions do we have here? Just one example. So let's make it f of xy, that's u of xy. I don't relate to free numbers, I just relate to the function. U of xy is what do you want here? Let's say y minus sine of x. Okay. And then take the first part of this. So the picture is like this. So y is, the sine function is something like this. Y minus sine x positive is here. So your function is positive here, and then it's 0. I can power it to 2. I can power it to something else. It's a good function. I have nothing to do with phenomenon for the moment. I'm just looking at the zoom technique. I can zoom the problem here, function here. I can zoom it here. So let's take its origin because it's simpler in computation. If you're doing other places, then you have to compute a little bit more. So let's make that origin to simple. So if you want to zoom this at the origin, you go for x is z0, x1 and x2, let's say. x2 minus x1. Simple. So if you zoom this, what happens? You have u of rx, that's going to be r x2 minus sine of r x1 to power and plus power alpha. So when r goes to 0, what happens with this? It goes to 0. Okay, that's the little news. That's definitely bad news. Because in the limit, I have nothing to work with. When r goes to 0, this ur, so this function u of r, equals to this, disappears. I have nothing to work with. So let us try with dividing by something. We divide by r to power a. It's not that alpha, it's a. Then I'm going to get what? I'm going to get this r to power a. And this will again disappear from the picture if alpha is larger than a. Because what you have there is linear. This is almost like r. It's linear. R to power alpha. When alpha is larger than a, this goes to 0. When alpha is less than a, it goes to infinity. So what you have to choose is a equal to alpha. If you choose a equals to alpha, then actually in the limit, so the best choice then you get, this gives you get ur is like r, well, it just disappear with each other, x2 minus sine of rx1 divided by r alpha, alpha here, and they're equal, so r is 1, therefore r is, okay, there's an r here, and what is this function going to when r goes to 0? That goes to x1. And what you get in the limit is actually, if I may take this out now, what you get in the limit is u r converged to 0, which is x2 minus x1 plus, and then also power. And that's the actual line. This is your function, the limit function. But now realize that if this would be our problem, then I'm ending up with a very nice problem in half space. Okay? And I can work with it. Still, this doesn't have any PDE in it, but we can use this idea and apply it for a PDE problem. If your problem was a little bit different, if you would have 1 over x, 1, then you see that you might be in trouble. So you might be in trouble. But when you have such a thing, actually these things do not appear in that problem, because the Laplacian problem is very good. The Laplacian of this is like 1 over x squared, so it's not so good. So our problem, PDE now, doesn't allow such examples. It allows actually good examples. Okay, so let's not go further into this, but this is the idea. This is the idea. You have to scale it. So I want to scale this, so let me erase this example here. I want to scale it. And this is my UR. And if I want to scale it, it means that this is not enough, good enough, so I have to divide it by R to power A. Now I have to choose what A is. In my examples, I saw what A is. But this is a little bit more general. So, first of all, I know that that's going to be bounded by R squared. Why is it around here? So, it's going to be R. So, this is less than equal. I know that this is less than R to the power 2. Okay? When I say less than equal, there's a constant here. In order for this to stay bounded, I don't want to bound the functions in the limit. So this tells me that A is less than equal to 2.
You wanted R cube, no? Aren't you considering it goes faster? Aren't you looking at?
Oh, yeah, okay. Change my idea of proof. Yeah, no, I was waiting for it too. Well, I was going to exemplify it, but then I tried to change my idea during the course of improvising. Okay. So forget it. I already showed you that. So what you get here is already 8 less than 2. Okay. So 8 is less than 2 because you can never get R3 because R3 is not so good. Sorry, I didn't say this. Yeah, it could be R3. Sorry. Let me change this. It can be that R to power 3. Then I can allow A to be 3. But I don't know that. So what I have to do is to look at this and say, what exactly I can do with it. So the first thing is the Laplacian of UR is what? R to power 2 comes out, and then you have R to power A. And then you have Laplacian of U at the point Rx plus C. But this is a characteristic function of escape function, meaning Rx plus Z is positive. So but you can rewrite this like you are, this is positive, it's the same thing. So what you have is equality with R2 minus A characteristic of U1 is positive. So this is what you get. You compute it, this is exactly the answer. The question now is, what should A be? Okay. If A is larger than 2, if it's, let's say, 3 or something like that, then I have a problem here, because I'm dividing the right-hand side divided by r, basically, if a is 3. So, if a is larger than 2, then it is almost like infinite times characteristic function. When r is very small. If a is less than 2, it's almost 0 times characteristic function. Approximately. So in either case, I have trouble here. So I have to choose a is 2 is okay. Okay, so a is 2 is okay. But now what I have to do is to prove that really a equals 2. So my function will go faster, if it would go fast to 0, then this is not going to, faster than 2, then this is not going to work. Am I correct? Yes. So this is not going to work. So an example of a equals to 3 would give me what? Would give me u is approximately r to the power 3, then u of rx is z divided by r, whatever a is like r to the power 3, and then r to the power a. So in order for this to survive, I have to take a to be 3. But then that's not going to be bounded. That's going to be another true. So a2 is the correct answer here. If I take a equals to 2, then this guy will go to 0. This again is a problem. So the only chance for me to work with this is to prove that my supremo is like r to the power 2. Then I'm exactly in balance. So I have to prove supremo is a power 2. R to the power 2.
So does it mean that it can never be bigger than 2?
Sorry, what?
Does it mean that it can never be bigger than 2?
2?
Only because that the method.
No, it can be larger than 2, but we are sort of preventing that by assuming something on the function f.
Okay.
If you remember, I assumed f is larger than lambda 0, larger than 0.
Yes.
That's an important one. If f is 0, at some points f becomes 0, exactly at that point you can have better regularity, faster to 0. So if f is 0, it means Laplacian is going to 0. So there's a good chance that second derivatives are going to 0. Second derivative is going to 0, it means that u is like r to the power 2 plus something going to 0. But if f is strictly positive, it means that these some of the second derivatives survive. They don't go to 0. So it's like r to the power 2. So I'm saying u should be like R2, it's supremum here. Should be like R2. This is true for case. We have the right hand side, and we assume that this is larger than lambda 0, larger than 0, but not in general. If f is 0 at some points on the free boundary, then the function already suggests that second derivatives have to go to 0 very fast. At least the Laplacian goes to 0 fast. And you can get for regularity for you, much better regularity for you at that point, and that's not what you want. Okay, so this is the heuristic idea. Let's see how it works with the slide. So let's go to the slides. Let's see how the proofs of these things are. So now I'm repeating, I give you a little bit of time to read the slide. So here, this was the assumption we had. That's very important. So I'm saying I have to go with KR2 and not faster or better. Because if it's better than I'm the problem becomes a different problem. Actually, there are other class of problems when, let's say, Laplacian of U is U, let's say, plus parallel. That's a nonlinear problem. Then already it goes to zero fast. So you don't have that scenario. But here, then you jump into the next level. The functions become C to 1. And then your scaling should be like R to power 3. Or maybe not 3 itself, but something like that. It still can work. But it will be different scale. You have fly going around here, it's hopefully it's just a fly.
Yeah, it is.
It's a fly.
A big one.
Catching with some crickets.
No, not crickets.
You get crickets?
At night, maybe.
Okay, so non-degeneracy. Here's the claim I have. That lambda 0 is 1 for us, in general. So if this is argument lambda 0, and you get the lambda 0 here, so we can think of it to be 1. So I'm claiming that supremum is actually like R to power 2. It cannot go below that. The proof is not so hard, it's actually elementary. But I want you to remember this proof because I'm going to come back to a variant of this proof, a version of this proof later on, for something much stronger result that we will need. It's called directional monotonicity, which the proof is related to that and reminiscent of this.
So, let's go. So here, when you say non-degeneracy, you are calling this particular condition.
We call it non-degeneracy of order 2. Order 2 non-degeneracy. We call it non-degeneracy in this, but it's order 2. In linear problems, in linear non-degeneracy, like the Bernoulli problem and other problems, when your free boundary behaves like R to power 1, then the non-degeneracy is 1, order 1. In T-obstacle, for instance, you cannot pick the non-degeneracy, depending on what you have. So, and that's the non-degeneracy.
And also I wanted to ask, like when we already proved that the boundary is C11,
Yes.
the free boundary is C11.
No, not the free boundary, U's.
Oh, U is.
U, not free boundary. Hmm.
But then it would mean that the boundary is almost everywhere regular, right? Because
No.
it's from level 6 till.
No. This limit is. This is an example. You can think of the example I have in the paper by Gustav. No, you cannot. I don't know how anyway, but that example tells you that.
What I mean is that anyway, is the set, the free boundary is going to be the set. No, it is not equal to 0. It is boundary of.
Yes, boundary of a C11 function.
C11 function.
It's a boundary of C11 function can be anything. Just come up with an example. Take the function x2 minus sine of x1 where x1, and then play around with it.
Okay.
Yeah, I think we can get a lot of them. Non-degeneracy. So I want to prove that that it's going to be r to the power 2. Supremum is r to the power 2. Not better than that. It's a negative result, but that we need. The one proof is not so good. But this is what we need, because if I want to blow up, I need that to put a equals to 2 in order to get to the limit. Okay, the device is like this. You pick up at any point inside, not on the free boundary, but inside the memory. When you look at this function, so here's the picture for you. So here's the picture. Here's positive. Take a point here and look at the ball of radius r, and here it is. So u is positive on this side, u is 0 on this side. Does it fit on? So the reason I'm cooking this up is that Laplacian of u is 1 for its f. Then I should have a lambda 0 here instead. But since I'm taking f is to be 1, so just take this one. Laplacian of u is 1, and Laplacian of this function is also 1. So, and this is a constant, so Laplacian of the whole w is 0. It's a harmonic function when you're inside. So in this domain, it's a harmonic function. Agree? Because Laplacian of u is 1, then I'm not going over the boundary. I'm not going over the free boundary, I'm inside. And Laplacian of that function is 1, so they cancel each other. What else? W at the point x0 is 0. So W at x0 is 0. It's a harmonic function. So it allows me to deduce that harmonic function as a supremum, which is taken on the boundary, not inside. But inside we have a 0 value, so it means that maximum has to be larger than 0, otherwise it's violent. So supremum of W is on the boundary, and it has to be larger than or equal to 0. Okay? So maximum principle tells me that supremum is on the boundary and is larger than or equal to 0. But now, go back to your function. You take supremum here, it's like taking supremum here. So supremum of this function on the boundary, this is just a constant. This is on boundaries like r to the power 2, it's fixed. And then you get u, supremum of u, minus ux0 minus r to the power 2 is larger than or equal to 0. So you get supremum of w for a boundary of the r intersected with omega. Yeah, I probably jumped ahead here. Supremum is on the boundary. Okay, on the boundary, there are two boundaries. One part is this one, and one part is this one. Okay? One part of the boundary is this is the domain, and one is this. I know supremum is on the boundary, it has to be larger than or equal to 0. What about this boundary? What is the function u? 0. You have u0, u is 0. Minus ux0, but x0, u at x0 is positive. And then the other one is also, well, this is also, but the whole thing is going to be negative. So on this boundary, w is negative. But I'm claiming, according to a principle, or Maxwell principle, that supremum of W has to be larger than or equal to 0. So supremum doesn't happen here. It has to happen here. So if it happens here, on this part, then this guy is fixed constant, r to the power 2. The supremum of this guy will be supremum of W on the boundary of dr, which is supremum of U on the boundary of dr, minus U at 0, minus r to the power 2 divided by 12.
Which is greater than 0.
And this is larger than or equal to 0. So it tells me what? It tells me supremum of U is larger than this guy. And if I let x0 go to the boundary, this goes out of the picture, and we get r to the power 2. This is the discussions I had. So this is negative on the boundary of omega, so therefore supremum is on the boundary of the ball of A plus R. And this is exactly what we do. This is larger than this, but then putting everything on this side, and you're going to get this one. But x0 is arbitrary on the boundary inside the domain. I can let it go to the boundary by continuing. It goes to the boundary, then it goes out of the picture, and you get supremum of U is larger than R squared if the point is on the free boundary. And that's exactly the claim I had. This is exactly the claim. The lambda 0, 1, of course. So that's the non-degenerate. So that tells me now that I really have this situation, that the function is really staying away from flattening out when I blow it up, which is very important. So conclusion so far is that supremum of U is going to be larger than C1 and R2, larger than C0 R2, less than C1 R2. So I'm sort of, if you're standing at 0 and you take a paraboloid, C1 R squared, and take a C0 R squared, your graph of the function U is in between. Okay? That's not the graph, the supremum of the function is in between. So the supremum is in between, not the graph. At some point, the function can be completely 0, but the supremum is always larger than R squared and between R squared. This actually helps us because of the invariant of the scaling that I tried to tell you there. That you scale it, you will have invariance. Invariance means that you still keep your PD. It doesn't change. It scales, but it doesn't change. Now you can realize that in the limit, by compactness, in the limit, you have a solution in the entire space. The entire R, and you have a solution, and that solution you want to study, you want to analyze. Whatever information you get there, you bring it back to the local problem and discuss it. Okay, so let me repeat the discussions I had on the board. So what we have here is, we are looking actually for such a possibility of scaling, is we want to zoom. And if you want to zoom, then you have to divide it by some r to the power a. In order to find a, correct one, you have to keep the PD. I don't want to lose my PD. I don't want to lose my function. So when I scale it, the answer will be this. Is everybody comfortable in showing that this is the scenario we get? Maybe we can do this. Practice on this, but this is just computation. Of course, A equals to 2, that's the only choice I have here. I cannot do anything else. So I have to prove it, and I already proved that I get this. Okay, so let me expand my discussion a little further. I think I have one example coming here. I don't remember it. So just remember that I have the supremum of U being between R squared larger than or equal to r squared. And 1 from above, if a is 2 there, 1 from above tells me that I have uniform boundedness of my sequence. So I have a sequence of functions ur, they're uniformly bounded. So I have this kind of Arzelov-Skolnik compactness. I can let r go to 0 for subsequence and get the limits in r in entire space. I have to prove that it is not going to flat out, and that I already proved because supremum is always larger than supremum of u is always larger than r squared, so it means supremum of ur is larger than some constant. So that doesn't flat out. So it survives. So I get the limit scenario. And that would be the global solution that I want to work with. And well, this is then repeating what I told already on the board. But if my function is like little o means that it goes faster. So it's little o power 2, then scaling. If you scale it at the point z, you're going to get this one and little o 1, and that goes to 0. That we don't like. So you need this non-degeneracy. You need to prove it. I thought I had an example, but I don't see it here. I think it's coming later on, yeah. Okay. So I think I will finish with one regularity of the free boundary here, and that's the level measure of the free boundary. So that's we call it low regularity of the free boundary. So I can prove that the free boundary has this low regularity. It has positive measure of 0 here. And in this setting, I claim it doesn't have a positive measure. Of course, this is like asking, well, almost asking the obvious. If you're talking about a boundary, why should a boundary have positive volume, positive direct measure? Of course, they can have. We can have boundaries so we can have a domain whose boundary has positive direct measure. So maybe for you it would be a good exercise to just find those examples. Find an example that is possible. So explicit examples. Okay. An explicit example of a domain which has positive direct measure. Tomorrow I will go into the Hausdorff one. I will not define again Hausdorff, but I will do something that's easier just to understand. Okay, so let's look at the Lebesgue. So for you would be to find an example of a domain whose Lebesgue measure is, whose boundary has a positive Lebesgue measure. Okay. So what we have is that the Lebesgue upper density of a set. I think this was also one of the exercises or something. With almost all points of E satisfy this, the lim sup of this guy is 1. That's called Lebesgue upper density. That's your Lebesgue measure course. But maybe you didn't do this. I think they don't, yeah. You don't do this, but that's, it could be this is an exercise in Lebesgue course.
Yeah.
But they're not as hard exercises maybe. Okay, so I would suggest that we look at this. So, look at Lebesgue upper density. It's in Wikipedia, you can find, Math Wikipedia, you can find a lot of stuff about this. Just, I mean, you don't need to read the proofs, but maybe understand it. Depending on your future, you might need. So this we have to use in order to prove Lebesgue measure is 0. Because what we're going to prove is that if you take, so I'm going to replace E with the free boundary, and I'm going to show that if I replace E with the free boundary, I don't get 1, I get less than 1. Since that this theorem tells me that the measure of gamma has to be 0. Because if almost everywhere should be 1, if it's always less than 1, so It means that the measure has to be 0. So so here's the proof for that. Okay. So take a point, I will need the board here. So take a point. I will get this. Take a point on the free boundary. Take a ball of radius r, half r divided by 2. Well, it's not so important, but r divided by 2. So we know there is a point y r where supremum happens. The function takes supremum at least at 1. And I know that u at point r, yr, is controlled from below. That's the supremum point. So this is the supremum. I'm not writing supremum because it might happen a lot of points, but it's equal at least to the supremum. Agree? And this is larger than or equal to C0 r squared with r divided by 2 or something. If that's the old C0. And then, on the other hand, I know this is bounded by the distance, power 2. This is bounded by the distance, C1. The free boundary. The free boundary for omega plus. So what does it tell us? It tells us that if you stand here at the point yr, if you stand at the point yr, you go for the distance to the boundary. This is the distance to the boundary. Then this distance is larger than r to r, basically. If I just get rid of the 2's here, okay, so it says the distance is larger than r up to a constant. So it means the ball of radius, so this ball of radius, some constant times r, says the yr is inside the set when it is positive. So whenever you're taking a free boundary point, you take a ball of radius r or whatever, there's a proportional ball inside the domain omega. That's what I would prove, okay? I've proven that whenever you take a ball of radius r, the center of origin, there is a proportional, smaller ball but proportional to r, inside the set when it is positive. Okay? This is what we have to prove. So what does it mean? So let's go back to the Lebesgue point thing. How can I use that? So if you take the boundary of omega plus, free boundary, that's the E I wanted to talk about. If you take the E, intersecting with the ball of radius r, divided by dr, that's the density, that's going to be exactly equal to boundary of omega plus intersected with boundary of the same ball minus this ball here. We can take this out because boundary of omega plus is not intersecting this. Because it's inside, boundary doesn't intersect this. It's inside. So the volume, the measure of this set intersected with this is the same as this intersected with this. Because this set doesn't never see this, or you can take it out, it doesn't care. But now, get rid of this omega plus, the whole thing is less than the whole volume of this. The whole volume of this divided by this volume is of course less than 1, strictly less than 1. Because I've taken a ball of radius r, take smaller ball out, proportional, the volume is of course less than the volume of the whole ball, strictly, and divided by dr is less than 1. So going back to Lebesgue point, here. It says almost all x0 should be 1. But now I'm saying, wow, it's not working. So the set has to have direct measure 0. It's actually called porous because this gives you also dimension, but let's not go into that, that's very important. It gives you porosity. So it tells me that the Hausdorff dimension is less than actually n. I don't know what it is. It has to do with that constant C3. So you get that the free boundary is direct measure 0. So I suggest that you work out this piece here a little bit more, because this might be even good for your basic courses you already have. It might be helpful. So go back to this and try to verify this in detail. Okay, so tomorrow we will look at the Hausdorff dimension. And in this setting, so let me tell you what the Hausdorff dimension is. Just so here is basically the Hausdorff dimension. What you do is you cover a set with Borel radius r, and then you take the minimum possible cover, minimum possible, and then sum up the radius, all radius. Let's say you have a line like this from 0, 1, take dimension 2. Dimension 2, take the line, a segment from 0, 1. How many balls do you need to cover ball of radius r? You need 1 over r balls. Let's say, how many balls do you need of radius 1 over n? You need n balls to cover it. Okay, so you have r to power 1 over n, r to power, I'm saying, you get, I'm more used to think of r rather than 1 over n. So you have 1 over n is the radius, that's r. And then how many do you need? You need n. That would be, if you take 1 over n to power alpha, if you take 1 over n to power alpha, and then you take n balls to cover it, if alpha is less than 1, n goes to 0, this goes to infinity. If alpha is larger than 1, this goes to 0. So that tells you already the dimension of this 1. Alpha should be 1 to get the constant. So that's the Hausdorff thing. Okay, and now it doesn't really need to be a segment. It can be very nasty.
You have to repeat it again tomorrow.
I'm going to feel it. You're all tired. Okay. Okay, thank you. Repeat it tomorrow. So, I'm going to go back for a few minutes or
I
something.
will take it. So when the KBC's driver will come to pick up class.
Tomorrow? What?
10:30. Kidnapping you.
More talks? Just to make a repeat from today. So.
Yeah, and they will not invite you again.
Nothing like it.
I'm not invite you
I think
again.
that's a good idea. Usually. You can do that in your course. You take the hard stuff at the beginning. Most students that. Listen to the very.
Unfortunately, they do not have a how do you say? All courses are compulsory. And if you don't have more than 5 students, then a course is not run.
Nice.
Somebody did try that 2 years ago. But he didn't succeed.
You're still here. You seem to be very. You seem to be like workaholics. Okay, sorry for today. We're disappointed, I was sorry.
They need to change what their mathematics is, so that, you know, when
We are not
they
we're
get
not
humbled.
there yet.
Okay, yeah, they get humbled, you know, people should not think that we know so much, like.
We are not there yet. We think on the last day, it's just fun. We try to keep them to last. We don't know what it's on. So trust me, that's why we're not there trust. We're really not. Not talking about at the basic level, mostly playing geometric. I'm trying to skip technicals here, but